Welcome back. In my previous video, I had seen what is the Liouvillie theorem, what is the extension of Liouvillie theorem. In my previous video, I had seen extension of Liouvillie theorem is an entire function f which satisfies modulus of fz less than equal to capital M times mod z to the power alpha for some alpha greater than equal to 0 and m greater than 0, all sufficiently large mod z, then this reduces to a polynomial of degree n, where obviously this n is the largest integer such that n less than equal to alpha. This is the extension of Liouvillie theorem. In my previous video I had seen. Also I had seen if f which is defined from complex to complex and alpha greater than 0 and r greater than 0 such that absolute value of modulus of fz less than equal to k times mod z to the power alpha, and this is true. Notice, this is true for all modulus of z less greater than r. Then fz is polynomial at most alpha. This is the extension of Liouvillie theorem. That means by extension of Liouvillie theorem, since extension of Liouvillie theorem and entire function f, so obviously f is entire, and here modulus of fz less than equal to k times mod z to the power alpha, and this is true for all modulus of z greater than r. Okay, then we can tell this is polynomial at most r. That means this is true for mod z greater than r, but function is also analytic on mod z less than equal to r, because the function is entered in whole complex plane. Then by this inequality we can tell by Cauchy's estimate formula, fn0, that means derivative of the function, n derivative of the function at the point 0 is less than equal to m n factorial modulus of z to the power alpha over r to the power n. And since this is true for all modulus of z greater than r, so on this boundary this value would be mod r to the power alpha over r to the power n. That means this is less than equal to m n factorial r to the power n minus alpha. And when n tends to infinity, then this value goes to 0. That means those value of n which is greater than alpha, then n derivative of the function at the point 0 would be 0 when n greater than alpha. That means by this inequality we can tell there exists a polynomial at degree at most alpha, and this is the extension of Liouvillie theorem which I had discussed in my previous video. If you don't see my previous video at first, I will highly recommend you please see my previous video, then today's video would be so easy. Here one more thing noticeable. This inequality is true for all z greater than r. If we increase the value, at first take this type of r, this type of region, if we increase the value, that means if r goes to infinity, then this value also goes to 0. That means when r goes to infinity, n derivative at the point 0, the value would be 0. So there exists only be polynomial at most alpha. As for example, next I will see one example. Let fz be analytic such that mod fz less than equal to m times mod z whole square. And this is true for all z greater than equal to r. Then obviously fz be a polynomial of degree 2. Is it correct answer? At first think. Just think. Here fz is analytic. Therefore, when we can take the large value r, if we take r goes to infinity, then we cannot tell about analyticity of fz, because here fz is not entered, here fz is analytic. So we cannot tell about this fz be polynomial of degree 2. So this answer is wrong answer. Obviously this is true. Fz is polynomial of degree 2 when the given fz is entire function. I hope my all viewers have understood this is okay. Next, in my previous video I had seen the use of Liouvillie theorem and extensions of Liouvillie theorem. In my previous video I had seen what is the consequences of fundamental theorem of algebra. In my previous video I had seen polynomial can be factored in complex number. That means pz equal to an z minus z1 z minus z2 up to z minus z8 zn, where these z1 z2 zn are zeros of the polynomial. We can factor pz such type. Obviously this is not necessarily distinct. If we consider px equal to x square plus 1, then we all of us know this has no zeros in R, because this cannot be factored in R. But if we consider pz equal to z square plus 1, then we can factor this as z plus I times z minus I, because here the root are I minus I. So in polynomial can be factored always in complex number. Obviously this root not be necessarily distinct. I hope my all viewers have understood. In my previous video I had discussed this part elaborately. Today's goal of this lecture actually, today I will see what is the maximum modulus theorem. At first I will see some example of extension of Liouvillie theorem and Liouvillie theorem. Then I will see the maximum modulus theorem. This is be the today's goal of this lecture. Okay? See some more exercise about generalized Liouvillie theorem. Okay? Next I will see one exercise about extensions of Liouvillie theorem. The exercise is the image of non-constant entire function always is dense in the complex number. That means, in other words, given W0 belongs to complex number, there exists a sequence Zn in complex number such that image goes to W0, where Obviously, this f is a non-constant entire function. I hope my all viewers have understood. And this type of question actually I had discussed in my previous video, but in here I will prove it by contradiction. Suppose there exists one W naught which is not in the closure FC. That means which is not in the image of the function. Image of the function means set of all value of the function. That means there exists epsilon greater than 0 such that modulus of fz minus w naught greater than equal to epsilon. That means absolute value of w minus w naught less than epsilon, where w naught is the outside of the closure of the set which does not intersect the image. Now obviously this fz minus w naught is an entire function and non-vanishing. So since fz minus w naught is entire and non-vanishing, so 1 over fz minus w naught is also entire and non-vanishing function. Therefore, that implies I have got absolute value of fz minus w naught greater than equal to epsilon, because I have considered w naught is not in the image of the function. So that implies 1 over fz minus w naught, this absolute value is less than equal to 1 over epsilon. So since this is less than equal to epsilon, so f be constant by Liouvillie's theorem. Okay, but here given the function f is non-constant entire function. Therefore, our assumption is wrong assumption. I have assumed there exists w naught which is not image of the function. Therefore, our assumption is wrong. That means obviously there exists one w naught which is the member of image of the function. So the image of non-constant entire function is always dense in the complex plane. I hope my all viewers have understood. Hence, given w naught, there exists a sequence Zn in complex number such that these fZn converges to w naught. Okay. Oh well. Next, let fz equal to uxy plus ivxy be an analytic function on the complex plane C, and the condition such that vxy greater than equal to y. Then which of the following statement is true? Option 1, f is 1 1, option 2, f is 1 2, and option 3, range of f is dense in the complex plane, and option 4, f is constant. And this question had come in session net exam. At first, try to oneself. Here given condition vxy greater than equal to y. For this, consider one new function gz equal to e to the power I fz minus iz. E to the power I fz minus iz means e to the power I times fz minus z, which is equal to e to the power I times u plus iv minus I x plus iy. This is equal to e to the power iu minus v minus ix plus y. That means this is equal to e to the power minus v plus y plus I times u minus x. That means z equal to e to the power minus, here would be v minus y times cos u minus x plus I sin u minus x. Okay? And if we apply modulus both sides, then this would be modulus of cz equal to e to the power minus v minus y absolute value of cos square u minus x plus sin square u minus x. That means this value would be e to the power minus v minus y. And since here given vxy greater than equal to 0, that means v minus y greater than equal to 0. And for this condition, here I have considered zz equal to e to the power I fz minus iz. I hope my all viewers have understood this is. Since v minus y greater than equal to 0, that imply minus v minus y less than equal to 0. That means absolute value of mod zz less than equal to 1, modulus of zz less than equal to 1. That means entire plus bounded. That implies the function is constant, zz function is constant. That means e to the power I times fz minus z, this is equal to constant k. So this imply I times fz minus z, this value is equal to log k. That imply fz minus z, this value is equal to minus I log k. So that imply fz equal to z plus, consider this minus I log k, this constant, consider a. So obviously this is be the polynomial of degree 1. Image of the f is the polynomial of degree 1. So f is 1 1, f is 1 2, and range of f is dense in the complex plane. I hope my all viewers have understood this question. Okay? Oh, yeah. Now I will see our actual goal of this lecture. Maximum modulus principle. What is the maximum modulus principle? Suppose f is analytic in a neighborhood of a point z0 and consider the ball of epsilon radius. Consider this neighborhood n epsilon z0 such that modulus of fz less than equal to modulus of fz0, and this is true for all z belongs to in this ball. Then always f is constant in this ball. That means fz equal to fz0, this is true for all z belongs to n epsilon z0. That means a non-constant analytic function cannot attain the maximum value in this neighborhood. At first I will say proof of this theorem. If there exists any maximum value in the interior point, then that implies obviously the function is constant function. And the proof is very easy type proof. Proof is such type. That means if you take non-constant analytic function, then it cannot maximum in the interior point. For this, consider z1 be the arbitrary point and consider this ball in epsilon z0. That means consider this epsilon ball and consider z1 be the arbitrary point in this ball. Now draw a circle at z0 passing through z1 with radius gamma. Have you understood? That means distance between z0 minus z1, absolute value of z0 minus z1 is, consider not gamma, consider this rho. That means draw a circle z0 passing through a point z1. Consider then a circle 0 with center z0 passing through the point z1. And suppose absolute value of z0 minus z1 equal to rho. Now apply the Cauchy's integral formula to f on 0. Then we get fz0 equal to 1 over 2 pi I integration along 0 fz over z minus z0 dz. This is the Cauchy's integral formula. Now consider z equal to z0 plus rho e to the power I theta. Now put the value, this value would be 1 over 2 pi I. Here integration 0 to 2 pi f z0 plus rho e to the power I theta over rho e to the power I theta, and dz means I rho e to the power I theta d theta. Now cancel this part, then this value would be 1 over 2 pi I integration 0 to 2 pi f z0 plus rho e to the power I theta times I d theta. Now if we, and this value is fz0. Now if we modulus both sides, then this value would be modulus of fz0 equal to, this is less than equal to, this value would be less than equal to, just cancel this I and this I, then this value would be less than equal to 1 over 2 pi integration 0 to 2 pi f z0 plus rho e to the power I theta, here absolute value d theta. Then now indicate this is 1 since z0 plus rho e to the power I theta belongs to n epsilon z0, this neighborhood. Therefore f z0 plus rho e to the power I theta, this image, this value always less than equal to absolute value of f z0. Okay, then if we integration both sides, then this value would be, now if we integrate both sides, then this value would be absolute value of integration 0 to 2 pi f of z0 plus rho e to the power I theta d theta less than equal to integration 0 to 2 pi absolute value of integration 0 to 2 pi f z0 d naught, and this value would be equal to absolute value of f z0 2 pi. Therefore this value 1 over 2 pi integration 0 to 2 pi modulus of f z0 plus rho e to the power I theta d theta less than equal to modulus of f z0, and just indicate it 2. Now from 1 and 2, we can write this as f z0 equal to, just notice this is the 1 and this is 2. So from 1 and 2 we can write f z0 equal to 1 over 2 pi integration 0 to 2 pi absolute value of f z0 plus rho e to the power I theta d theta. Okay, therefore, and this is the absolute value of f z0. Therefore from this we can write this as, since this value is 1 over 2 pi, if we change this here, so this would be, we can write integration 0 to 2 pi absolute value of fz naught minus absolute value of fz naught plus rho e to the power I theta d theta equal to 0. I hope my all viewers have understood, and this is the non-zero integrand whose value is 0, and this is the since fz less than equal to fz naught, so this is the non-negative part whose value is 0. This is the non-negative integrand whose value is 0. So that imply these two value is equal. Absolute value of fz naught equal to absolute value of fz naught plus rho e to the power I theta. So since these two value equal, that means that imply the function f is constant. I hope my all viewers have understood the maximum modulus principle and proof of the maximum modulus principle. That means this is constant because modulus of fz is constant in the neighborhood n epsilon z naught. Okay, therefore f is constant in n epsilon z naught. Okay, then what is the next version of maximum modulus principle? Next version of maximum modulus principle is, let consider D be a bounded domain. Obviously this is necessary condition, and suppose fz is analytic and non-constant in this domain and continuous on this domain. Since the domain is bounded and the function is analytic and non-constant, bounded means by maximum principle there exists always be a bound, maximum bound, and these bound exist. The absolute value of modulus of fz attains in its maximum on the boundary T. I hope my all viewers have understood. The second version of maximum modulus theorem is, when the function is non-constant, then its maximum value exists only on the boundary T. That means actual maximum modulus principle is, another version of maximum modulus principle is, if fz is analytic function inside on a simple closed curve C, then its maximum value means modulus of fz occurs on this curve C unless the function fz is constant. I hope my all viewers have understood. For example, consider the domain D equal to Z such that modulus of Z less than equal to R. Then the question, here the function is e to the power Z, then the question, what is the maximum value of this function? Since maximum, so here I have applied the modulus on this domain of this function on this domain. Since here D equal to Z such that modulus of Z less than R, in this domain there exists no Z naught such that e to the power modulus of e to the power Z less than equal to e to the power Z naught, modulus of e to the power Z naught, and this is true for all Z belongs to the domain D. Then what I will do? What is the maximum value of the function e to the power Z? E to the power Z, modulus of e to the power Z means e to the power x plus iy, which is equal to e to the power x modulus of e to the power x times e to the power iy, and this value is 1, that means this is equal to e to the power x. So by maximum modulus theorem we can tell in this domain only maximum value exists on the boundary. So this value is e to the power, absolute value of e to the power r. I hope my all viewers have understood. Modulus of e to the power r means e to the power r. So this value is e to the power r. Similarly, for non-constant function sin z, cos z, similarly we can find the maximum value in this domain on the boundary, but the value would be, if you consider fz equal to cos z, then maximum value of on this domain modulus of z less than equal to r, absolute value of cos z, this value would be cos hyperbolic r. And why cos hyperbolic r? Just try own self. If you can to find cos hyperbolic r, then do comments in comments box. I will solve in my next video also. Okay? Today I will stop here. In my next video I will discuss more exercise based on maximum modulus theorem. But at first I will highly recommend you, please see today's video with pay attention. Okay? See you soon, stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.